All right, today we're tackling something that is absolutely 100% critical for anyone running simulations: element quality in finite element analysis. If you've ever wanted more accurate, stable results, and you definitely want to avoid those super frustrating solver errors, then you need to master this. So let's jump right in. You know the feeling, right? You spend hours, maybe days, getting your model just right. The boundary conditions, perfect. Material properties, correct. The physics setup, spot on. You hit solve and nothing. It either fails to converge or it spits out results that are complete nonsense. It's probably one of the most maddening experiences in all of engineering analysis. So what is really going on under the hood?
Well, the answer, more often than you'd think, is hiding in plain sight. It's your mesh. And it's not about how many elements you have, it's about how good they are. This is the world of element quality. And trust me, understanding it is the key to getting reliable simulations.
So, here's our game plan. First, we're going to dig into why quality is so important in the first place. Then, we'll walk through the 5 most important checks you'll be using every single day, from aspect ratio to the make-or-break Jacobian. And to wrap it all up, we'll finish with a super practical cheat sheet that you can use on your own projects.
Okay, first things first. Before we get into all the numbers and the metrics, we really need to understand the fundamental reason why one badly shaped element can bring a whole simulation to its knees.
So what even is element quality? The easiest way to think about it is like a report card for every little shape in your mesh. The software gives each triangle, quad, or tetra a score, usually from 0 to 1. A perfect 1.0 means it's an ideal, beautiful shape, like a perfect equilateral triangle. A score down near 0? That means it's badly distorted, maybe even completely collapsed.
And just look at the difference here. On the left, a perfect element. The solver's internal math loves this. It works perfectly. But on the right, you've got this slivered triangle. This thing is a solver's worst nightmare. The math required to map this real, ugly shape back to a perfect reference shape becomes incredibly unstable. And that instability just magnifies tiny numerical errors until they explode and completely wreck your solution.
Okay, let's dive into our first specific metric. This is probably the most intuitive one to get your head around: the aspect ratio. Aspect ratio is pretty much exactly what it sounds like. You take the longest side of an element and divide it by its shortest side. For a perfect square or a perfect equilateral triangle, all the sides are equal, so the ratio is 1. And that's our gold standard. And this right here shows you why it matters so much. Imagine that colorful wave is something you're trying to measure, like a temperature or a stress gradient. In the element on the left, with its nice low aspect ratio, the solver can capture that gradient accurately, no problem. But now look at that long stretched out element on the right. When the gradient you're interested in runs across its short direction, the solver has almost no data points to work with. This leads to massive interpolation errors and results you just can't trust. So what are the practical rules of thumb? Generally speaking, you want to keep your aspect ratio below 5 to 1. If you see anything creeping above 10, that should be a huge red flag. Now there is one really important exception. In computational fluid dynamics, or CFD, engineers will actually deliberately create high aspect ratio elements right near a surface to build what's called a boundary layer mesh. It's a special case, but a very important one to know about.
All right, next up are a couple of metrics that are all about the angles inside your elements. Let's talk about skewness and orthogonal quality.
Skewness basically tells you how lopsided or squished an element's angles are. A perfect triangle has all 60-degree angles, and a perfect quad has all 90-degree angles. The more your element deviates from that, the higher its skewness score gets. Now, here's a key thing to remember. For skewness, 0 is perfect and 1 is the absolute worst, so low is good. Now, orthogonal quality is a very similar idea, and it's the #1 metric for most CFD solvers. It's checking how perpendicular the faces of an element are to an imaginary line drawn to its center. But notice the range is the exact opposite of skewness. Here, a score of 1 is the best you can get, and 0 is the worst. This metric is absolutely crucial for calculating things like pressure in a fluid flow simulation.
So what are the magic numbers you need to remember? For skewness, you really want to keep everything below 0.85. For orthogonal quality, you want to stay above 0.1. If you start dipping below these thresholds, especially in CFD, you're just asking for inaccurate results or a solution that blows up.
All right, we need to pause and talk about the most important check of them all. Seriously, if you only remember one metric from this entire explainer, please make it this one, the Jacobian. Remember how we said the solver maps your real physical element back to a perfect one? Well, the Jacobian is the score that tells us how good that mapping is.
A perfect score is 1. As your element gets more and more distorted, that score drops and drops.
But here is the absolute deal breaker. If an element gets so twisted that one of its corners actually crosses over an edge, the mathing becomes mathematically impossible. The element has literally folded in on itself. When this happens, the Jacobian value goes negative. And this isn't an accuracy problem anymore. This is a fatal, show-stopping error. The element is physically impossible, and your solver will just stop, dead.
I really want this to sink in. There is no acceptable level of negative Jacobian. It's not something you can just ignore or work around. If your mesh checker flags a negative Jacobian, your first and only job is to find that element and fix it. End of story, no exceptions.
Okay, let's round things out with our final 2 metrics. These look a little beyond just a single element and consider 3D effects and the overall flow of the entire mesh. First up is warp angle, and this applies only to 4-sided faces, like quads. See, any 3 points will always form a flat plane, but a 4th point can easily pop out of that plane, creating a warped potato chip shape. Mesh smoothness, on the other hand, is a global check. It's not about one element, it's about the relationship between neighboring elements and how quickly their size changes.
For warping, the general rule is to keep that angle below 45 degrees. Go much past that, and the solver just can't do its calculations accurately across that face. For smoothness, you want a nice, gentle transition between element sizes. A growth rate of 1.2 means an element is no more than 20% bigger than its neighbor. Think about it like reading a book where the font suddenly jumps from size 10 to size 30 in the middle of a sentence. It's jarring and really hard to follow. It's the exact same for a solver trying to follow a stress gradient across a sudden jump in mesh size.
Phew, we have covered a ton of ground. So now, let's boil it all down into a single, practical reference guide that you can use every day.
And here it is, your element quality cheat sheet. This table puts everything we just talked about in one place. You can see the ideal, the acceptable, and the problematic ranges for every key metric. Notice the clear thresholds for aspect ratio, the opposite scales for skewness and orthogonal quality, and right there in the middle, that absolute hard line for the Jacobian. It must not be negative. This is a great one to screenshot for your future reference. And if you walk away with nothing else, please remember these 3 golden rules. Rule number 1, never, ever, ever accept a negative Jacobian. That is the hard stop. Rule 2, when you're cleaning up a mesh, focus on improving skewness and orthogonal quality. That's where you get the biggest bang for your buck on accuracy. And finally, rule number 3, and this is so important, always choose quality over quantity. A coarser mesh with beautiful, well-shaped elements will almost always give you a better, more accurate, and faster solution than a superfine mesh that's filled with junk. At the end of the day, it's not about having more elements, it's about having the right elements.